Right, hello everyone. I am going to be today going over a piece that I wrote a few weeks ago called On the Nature of Time. Show you what it is. There it is. So let's launch here. On the nature of time, the computational view of time. Time is a central feature of human experience, but what actually is it? In traditional scientific accounts, it's often represented as some kind of coordinate, much like space, though a coordinate that for some reason is always systematically increasing for us. But while this may be a useful mathematical description, it's not telling us anything about what time, in a sense, intrinsically is. We get closer as soon as we start thinking in computational terms, because then it's natural for us to think of successive states of the world as being computed one from the last by the progressive application of some computational rule. And this suggests that we can identify the progress of time with the progressive doing of computation by the universe. But does this just mean that we are replacing a time coordinate with a computational step count? No, because of the phenomenon of computational irreducibility. With the traditional mathematical idea of a time coordinate, one typically imagines that this coordinate can be set to any value, and that then one can immediately calculate the state of the system at that time. But computational irreducibility implies that it's not that easy, because it says that there's often essentially no better way to find what a system will do than by explicitly tracing through each step in its evolution. So I have some pictures here that show elaborate patterns, and I'm showing first few pictures are rather simple, periodic kind of behavior. The next few look very elaborate, complex, intricate. So in the pictures that look simple, there's computational reducibility, and one can readily see what the state will be after any number of steps t. But in the pictures that are more complicated, there's sorry guys, I'm sharing the wrong thing. Let me go back and show you that again. So as I was saying, there's a collection of pictures here. The first ones are quite simple in their structure. The last few are much more complicated. So in the pictures that have a quite simple structure, one can readily see what the state of the system will be after any number of steps t. But in the pictures where there's more complicated behavior, there's presumably computational irreducibility, so that the only way to tell what will happen after some number of steps t is effectively to run all those steps. And what this implies is that there's a certain robustness to time when viewed in these computational terms. There's no way to jump ahead in time. The only way to find out what will happen in the future is to go through the irreducible computational steps to get there. There are simple idealized systems, say with purely periodic behavior, where there's computational reducibility and where there isn't any robust notion of the progress of time. But the point is that, as the principle of computational equivalence implies, our universe is inevitably full of computational irreducibility, which in effect defines a robust notion of the progress of time. The role of the observer. That time is a reflection of the progress of computation in the universe is an important starting point, but it's not the end of the story. For example, here's an immediate issue. If we have a computational rule that determines each successive state of a system, it's at least in principle possible to know the whole future of the system. So given this, why then do we have the experience of the future only unfolding as it happens? It's fundamentally because of the way we are as observers. If the underlying system is computationally irreducible, then to work out its future behavior requires an irreducible amount of computational work. But it's a core feature of observers like us that we are computationally bounded. So we can't do all that irreducible computational work to know the whole future, and instead we're effectively stuck just doing computation alongside the system itself, never able to substantially jump ahead and only able to see the future progressively unfold. In essence, therefore, we experience time because of the interplay between our computational boundedness as observers and the computational irreducibility of underlying processes in the universe. If we were not computationally bounded, we could perceive the whole of the future in one gulp, and we wouldn't need a notion of time at all. And if there wasn't underlying computational irreducibility, there wouldn't be the kind of progressive revealing of the future that we associate with our experience of time. A notable feature of our everyday perception of time is that it seems to flow only in one direction. So that, for example, it's generally much easier to remember the past than to predict the future. And this is closely related to the second law of thermodynamics, which, as I've talked about at length elsewhere, is once again a result of the interplay between underlying computational irreducibility and our computational boundedness. Yes, the microscopic laws of physics may be reversible, and indeed, if our system is simple and computationally reducible, enough of this reversibility may shine through. But the point is that computational irreducibility is, in a sense, a much stronger force. Imagine that we prepare a state to have orderly structure. If its evolution is computationally irreducible, then this structure will effectively be encrypted to the point where a computationally bounded observer can't recognize the structure. Given underlying reversibility, the structure is in some sense inevitably still there, but it can't be accessed by a computationally bounded observer. And as a result, such an observer will perceive a definite flow from orderliness in what is perceived, in what is prepared, to disorderliness in what is observed. In principle, one might think it should be possible to set up a state that will behave antithermodynamically, but the point is that to do so would require predicting a computationally irreducible process, which a computationally bounded observer can't do. One of the long-standing confusions about the nature of time has to do with its mathematical similarity to space. And indeed, ever since the early days of relativity theory, it seemed convenient to talk about space-time, in which notions of space and time are bundled together. But in our physics project, that's not at all how things fundamentally work. At the lowest level, the state of the universe is represented by a hypergraph which captures what can be thought of as the spatial relations between discrete atoms of space. Time then corresponds to the progressive rewriting of this hypergraph. And in a sense, the atoms of time are the elementary rewriting events that occur. If the output from one event is needed to provide the input to another, then we can think of the first event as preceding the second event in time, and the events as being time-like separated. And in general, we can construct a causal graph that shows the dependencies between different events. So how does this relate to time and space-time? As we'll talk about in a moment, our everyday experience of time is that it follows a single thread. And so we tend to want to parse the causal graph of elementary events into a series of slices that we can view as corresponding to successive times. As in standard relativity theory, there typically isn't a unique way to assign a sequence of such simultaneity surfaces, with the result that there are different reference frames in which the identifications of space and time are different. The complete causal graph bundles together what we usually think of as space with what we usually think of as time. But ultimately, the progress of time is always associated with some choice of successive events that computationally build on each other. And yes, it's more complicated because of the possibilities of different choices, but the basic idea of the progress of time as the doing of computation is very much the same. In a sense, time represents computational progress in the universe, while space represents the layout of its data structure. Very much as in the derivation of the second law, or of fluid dynamics from molecular dynamics, the derivation of Einstein's equations for the large-scale behavior of space-time from the underlying causal graph of hypergraph rewriting depends on the fact that we are computationally bounded observers. But even though we're computationally bounded, we still have to have something going on inside, or we wouldn't record or sense any progress in time. It seems to be the essence of observers like us, as I captured in my recent observer theory efforts, that we equivalence many different states of the world to derive our internal perception of what's going on outside. And at some rough level, we might imagine that we're sensing time passing by the rate at which we add those internal perceptions. If we're not adding to the perceptions, then in effect, time will stop for us, as happens if we're asleep or anesthetized or dead. It's worth mentioning that in some extreme situations, it's not the internal structure of the observer that makes perceived time stop. Instead, it's the underlying structure of the universe itself. As I've talked about, the progress of the universe is associated with successive rewriting of the underlying hypergraph. But when there's been too much activity in the hypergraph, which physically corresponds to too much energy momentum, one can end up with a situation in which there are no more rewrites that can be done, so that in effect, some part of the universe can no longer progress and time stops there. It's analogous to what happens at a space-like singularity, normally associated with a black hole, in traditional general relativity. But now it has a very direct computational interpretation. One's reached a fixed point at which there's no more computation to do, and so there's no progress to make in time. Multiple threads of time. Our strong human experience is that time progresses as a single thread. But now our physics project suggests that at an underlying level, time is actually in effect multi-threaded, or in other words, that there are many different paths of history that the universe follows. And it's only because of the way we as observers sample things that we experience time as a single thread. At the level of a particular underlying hypergraph, the point is that there may be many different updating events that can occur, and each sequence of such updating events defines a different path of history. We can summarize all these paths of history in a multi-way graph in which we merge identical states that arise. And we can see a graph where we have successive nodes in the graph where we branch and we merge those nodes. But given this underlying structure, why is it that we as observers believe that time progresses as a single thread? It all has to do with the notion of branchial space and our presence within branchial space. The presence of many paths of history is what leads to quantum mechanics. The fact that we as observers ultimately perceive just one path is associated with a traditionally quite mysterious phenomenon of measurement in quantum mechanics. When I was talking about causal graphs before, I said that we could parse these causal graphs as a series of space-like slices corresponding to instantaneous states of space, represented by spatial hypergraphs. And by analogy, we can similarly imagine breaking multi-way graphs into instantaneous slices. But now these slices don't represent states of ordinary space. Instead, they represent states of what we call branchial space. Ordinary space is knitted together by updating events that have causal effects on other events that can be thought of as located at different places in space. Or, said differently, space is knitted together by the overlaps of the elementary light cones of different events. Now we can think of branchial space as being knitted together by updating events that have effects on events that end up on different branches of history. In general, there's a close analogy between ordinary space and branchial space, and we can define a multi-way causal graph that includes both space-like and branch-like directions, with the branch-like direction supporting not light cones, but what we can call entanglement cones. So how do we as observers parse what's going on? A key point is that we are inevitably part of the system we're observing. So the branching and merging that's going on in the system at large is also going on in us. So that means we have to ask how a branching mind will perceive a branching universe. Underneath, there are lots of branches and lots of threads of history, and there's lots of computational irreducibility, and even what we can call multi-computational irreducibility. But computationally bounded observers like us have to equivalence most of those details to wind up with something that fits in our finite minds. We can make an analogy to what happens in a gas. Underneath, there are lots of molecules bouncing around and behaving in computationally irreducible ways. But observers like us are big compared to molecules, and being computationally bounded, we don't get to perceive their individual behavior, but only their aggregate behavior, from which we extract a thin set of computationally reducible fluid dynamics level features. And it's basically the same story with the underlying structure of space. Underneath, there's an elaborately changing network of discrete atoms of space, but as large computationally bounded observers, we can only sample aggregate features in which many details have been equivalenced, and in which space tends to seem continuous and describable in basically computationally reducible ways. So what about branchial space? Well, it's basically the same story. Our minds are big in the sense that they span many individual branches of history, and they're computationally bounded, so they can't perceive the details of all those branches, but only certain aggregated features. And in a first approximation, what then emerges is in effect a single aggregated thread of history. With sufficiently careful measurements, we can sometimes see quantum effects in which multiple threads of history are in evidence. But at a direct human level, we always seem to aggregate things to the point where what we can perceive is just a single thread of history, or in effect, a single thread of progression in time. It's not immediately obvious that any of these aggregations will work. It could be that important effects we perceive in gases would depend on phenomena at the level of individual molecules, or that to understand the large-scale structure of space, we'd continually be having to think about detailed features of atoms of space. Or similarly, that we'd never be able to maintain a consistent view of history, and that instead we'd always be having to trace lots of individual threads of history. But the key point is that for us to stay as computationally bounded observers, we have to pick out only features that are computationally reducible, or in effect, boundedly simple to describe. Closely related to our computational boundedness is the important assumption we make that we as observers have a certain persistence. At every moment in time, we're made from different atoms of space and different branches in the multiway graph. Yet we believe we are still the same us. And the crucial physical fact that has to be derived in our model is that in ordinary circumstances, there's no inconsistency in doing this. So the result is that even though there are many threads of time at the lowest level, representing many different quantum branches, observers like us can, at least usually, successfully view there as being a single consistent perceived thread of time. But there's another issue here. It's one thing to say that a single observer, say a single human mind or a single measuring device, can perceive history to follow a single consistent thread. But what about different human minds or different measuring devices? Why should they perceive any kind of consistent objective reality? Essentially, the answer, I think, is that we're all sufficiently nearby in branchial space. If we think about physical space, observers in different parts of the universe will clearly see different things happening. The laws of physics may be the same, but what star, if any, is nearby will be different. Yet, at least for the foreseeable future, for all of us humans, it's always the same star that's nearby. So it is, presumably, in branchial space. There's some small patch in which we humans with our shared origins exist. And it's presumably because that patch is small relative to all of branchial space that all of us perceive a consistent thread of history and a common objective reality. There are many subtleties to this, many of which aren't yet fully worked out. In physical space, we know that effects can in principle spread at the speed of light. And in branchial space, the analog is that effects can spread at the maximum entanglement speed, whose value we don't know, though it's related by Planck unit conversions to the elementary length and elementary time. But in maintaining our shared objective view of the universe, it's crucial that we're not all going off in different directions at the speed of light. And of course, the reason that doesn't happen is that we don't have zero mass. And indeed, presumably, non-zero mass is a critical part of being observers like us. In our physics project, it's roughly the density of events in the hypergraphs that determines the density of energy and mass in physical space with their associated gravitational effects. And similarly, it's roughly the density of events in the multiway graph or in branchial graph slices that determines the density of action, the relativistically invariant analog of energy in branchial space with its associated effects on quantum phase. And though it's not yet completely clear how this works, it seems likely that once again, when there's mass, effects don't just go off at the maximum entanglement speed in all directions, but instead stay nearby. There are definitely connections between staying at the same place, believing one is persistent, and being computationally bounded. But these are what seem necessary for us to have our typical view of time as a single thread. In principle, we can imagine observers very different from us, say with minds like the inside of an idealized quantum computer, capable of experiencing many threads of history. But the principle of computational equivalence suggests that there's a high bar for such observers. They need not only to be able to deal with computational irreducibility, but also multi-computational irreducibility, in which one includes both the process of computing new states and the process of equivalencing states. And so for observers that are anything like us, we can expect that once again, time will tend to be as we normally experience it, following a single thread consistent between observers. It's worth mentioning that all of this only works for observers like us in situations like ours. For example, at the entanglement horizon for a black hole, where branchially oriented edges in the multi-way causal graph get trapped, time as we know it in some sense disintegrates, because an observer won't be able to knit together the different branches of history to form a consistent classical thought about what happens. Time in the Ruliad. In what we've discussed so far, we can think of the progress of time as being associated with the repeated application of rules that progressively rewrite the state of the universe. What we talked about before was that these rules can be applied in many different ways, leading to many different underlying threads of history. But so far, we've imagined that the rules that get applied are always the same, leaving us with sort of the mystery of why those rules are not others. But this is where the Ruliad comes in, because the Ruliad involves no such seemingly arbitrary choices. It's what you get by following all possible computational rules. One can imagine many bases for the Ruliad. One can make it from all possible hypergraph rewritings or all possible multi-way Turing machines, but in the end, it's a single unique thing, the entangled limit of all possible computational processes. There's a sense in which everything can happen somewhere in the Ruliad. But what gives the Ruliad structure is that there's a definite, essentially geometrical way in which all those different things that can happen are arranged and connected. So what is our perception of the Ruliad? Inevitably, we're part of the Ruliad, so we're observing it from the inside. But the crucial point is that what we perceive about it depends on what we are like as observers. And my big surprise in the past few years has been that assuming even just a little about what we're like as observers immediately implies that what we perceive of the Ruliad follows the core laws of physics we know. In other words, by assuming what we're like as observers, we can in effect derive our laws of physics. The key to all this is the interplay between the computational irreducibility of underlying behavior in the Ruliad and our computational boundedness as observers, together with our related assumption of persistence. And it's this interplay that gives us the second law in statistical mechanics, the Einstein equations for the structure of space-time, and we think the path integral in quantum mechanics. In effect, what's happening is that our computational boundedness as observers makes us equivalence things to the point where we are sampling only computationally reducible slices of the Ruliad whose characteristics can be described using recognizable laws of physics. So where does time fit into all of this? A central feature of the Ruliad is that it's unique, and everything about it is abstractly necessary. Much as, given the definition of numbers, addition and equality, given that we've defined numbers, addition and equality, it's inevitable that one gets 1 + 1 = 2. So similarly, given the definition of computation, it's inevitable that one gets the Ruliad. Or in other words, there's no question about whether the Ruliad exists. It's just an abstract construct that inevitably follows from abstract definitions. And so at some level, this means that the Ruliad inevitably just exists as a complete thing. And so if one could view it from outside, one could think of it as just being a single timeless object with no notion of time. But the crucial point is we don't get to view it from the outside. We're embedded within it. And what's more, we must view it through the lens of our computational boundedness. And this is why we inevitably end up with a notion of time. We observe the Ruliad from some point within it. If we were not computationally bounded, then we could immediately compute what the whole Ruliad is like. But in actuality, we can only discover the Ruliad one computationally bounded step at a time, in effect, progressively applying bounded computations to move through Rulial space. So even though in some abstract sense the whole Ruliad is already there, we only get to explore it step by step. And that's what gives us our notion of time through which we progress. Inevitably, there are many different paths that we could follow through the Ruliad, and indeed every mind and every observer like us, with its distinct inner experience, presumably follows a different path. But much as I talked about before for branchial space, the reason we had a shared notion of objective reality is that presumably we're all very close together in Rulial space. We form, in a sense, a tight Rulial flock. It's worth pointing out that not every sampling of the Ruliad that may be accessible to us conveniently corresponds to exploration of progressive slices of time. Yes, that kind of progression in time is characteristic of our physical experience and our typical way of describing it. But what about our experience, say, of mathematics? The first point to make is that just as the Ruliad contains all possible physics, it also contains all possible mathematics. If we construct the Ruliad, say, from hypergraphs, the nodes are now not atoms of space, but instead abstract elements that in general we call eames that form pieces of mathematical expressions and mathematical theorems. We can think of these abstract elements as being laid out now not in physical space, but in some abstract meta-mathematical space. In our physical experience, we tend to remain localized in physical space, branchial space, and so on. But in doing mathematics, it's more as if we're progressively expanding in meta-mathematical space, carving out some domain of theorems we assume are true. And while we could identify some kind of path of expansion that lets us define some analog of time, it's not a necessary feature of the way we explore the Ruliad. Different places in the Ruliad, in a sense, correspond to describing things using different rules. And by analogy to the concept of motion in physical space, we can effectively move from one place to another in the Ruliad by translating the computations done by one set of rules to computations done by another. And yes, it's non-trivial to even have the possibility of pure motion. But if we indeed remain localized in the Ruliad and can maintain what we think of as our coherent identity, then it's natural to think of there being a path of motion along which we progress with time. But when we're just expanding our horizons to encompass more paradigms and to bring more of Rulial space into what's covered by our minds, so that in effect we're expanding in Rulial space, it's not really the same story. We're not thinking of ourselves as doing computation in order to move. Instead, we're just identifying equivalences and using them to expand our definition of ourselves, which is something we can at least approximate, much like in quantum measurement in traditional physics, as happening outside of time. Ultimately, though, everything that happens must be the result of computations that occur. It's just that we don't usually package these into what we can describe as a definite thread of time. So, what in the end is time? From the paradigm and physics project ideas that we've been talking about, the question, what is time, is at some level simple. Time is what progresses when one applies computational rules. But what's critical is that time can in effect be defined abstractly, independent of the details of those rules or the substrate to which they're applied. And what makes this possible is the principle of computational equivalence and the ubiquitous phenomenon of computational irreducibility that it implies. To begin with, the fact that time can robustly be thought of as progressing, in effect in a linear chain, is a consequence of computational irreducibility, because computational irreducibility is what tells us that computationally bounded observers like us can't in general ever jump ahead. We just have to follow a linear chain of steps. But there's something else as well. The principle of computational equivalence implies that there's in a sense just one ubiquitous kind of computational irreducibility. So when we look at different systems following different irreducible computational rules, there's inevitably a certain universality to what they do. In effect, they're all accumulating computational effects in the same way, or in essence, progressing through time in the same way. There's a close analogy here with heat. It could be that there'd be detailed molecular motion that even on a large scale worked noticeably differently in different materials. But the fact that we end up being able to characterize any such motion just by saying that it represents a certain amount of heat without getting into more details. And that's very much the same kind of thing as being able to say that such and such an amount of time has passed without having to get into the details of how some clock or other system that reflects the passage of time actually works. And in fact, there's more than a conceptual analogy here, because the phenomenon of heat is again a consequence of computational irreducibility. And the fact that there's a uniform abstract characterization of it is a consequence of the universality of computational irreducibility. It's worth emphasizing again, though, that just as with heat, a robust concept of time depends on us being computationally bounded observers. If we were not, then we would be able to break the second law by doing detailed computations of molecular processes, and we wouldn't just describe things in terms of randomness and heat. And similarly, we'd be able to break the linear flow of time, either jumping ahead or following different threads of time. But as computationally bounded observers of computationally irreducible processes, it's basically inevitable that at least to a good approximation, we'll view time as something that forms a single one-dimensional thread. In traditional mathematically based science, there's often a feeling that the goal should be to predict the future, or in effect to outrun time. But computational irreducibility tells us that in general we can't do this, and that the only way to find out what will happen is just to run the same computation as the system itself, essentially step by step. But while this might seem like a letdown for the power of science, we can also see it as what gives meaning and significance to time. If we could always jump ahead, then at some level nothing would ever fundamentally be achieved by the passage of time, or say by the living of our lives. We'd always be able to just say what will happen without living through how we got there. But computational irreducibility gives time and the process of passing a kind of hard, tangible character. So what does all this imply for the various classic issues and apparent paradoxes that arise in the way time is usually discussed? Let's start with the question of reversibility. The traditional laws of physics basically apply both forwards and backwards in time, and the Ruliad is inevitably symmetrical between forward and backward rules. So why is it then that in our typical experience, time always seems to run in the same direction? This is closely related to the second law, and once again, it's a consequence of our computational boundedness interacting with underlying computational irreducibility. In a sense, what defines the direction of time for us is that we typically find it much easier to remember the past than to predict the future. Of course, we don't remember every detail of the past. We only remember what amounts to certain filtered features that fit in our finite minds. And when it comes to predicting the future, we're limited by our inability to outrun computational irreducibility. Let's recall how the second law works. Basically says that if we set up some state that's ordered or simple, then this will tend to degrade to one that's disordered or random. We can think of the evolution of the system as effectively encrypting the specification of our starting state to the point where we as computationally bounded observers can no longer recognize its ordered origins. But because our underlying laws are reversible, this degradation or encryption must happen when we go both forwards and backwards in time. But the point is that our experiential definition of the direction of time, in which the past is what we remember and the future is what we find hard to predict, is inevitably aligned with the thermodynamic direction of time we observe in the world at large. And the reason is that in both cases, we're defining the past to be something that's computationally bounded, while the future can be computationally irreducible. In the experiential case, the past is computationally bounded because that's what we can remember. In the thermodynamic case, it's computationally bounded because those are the states we can prepare. In other words, the arrows of time are aligned because in both cases, we're in effect requiring the past to be simpler. So what about time travel? It's a concept that seems natural and perhaps even inevitable if one imagines that time is just like space. But it becomes a lot less natural when we think of time in the way we're doing here as a process of applying computational rules. Indeed, at the lowest level, these rules are by definition just sequentially applied, producing one state after another, and in effect progressing in one direction through time. But things get more complicated if we consider not just the raw lowest level rules, but what we might actually observe of their effects. For example, what if the rules lead to a state that's identical to one they produced before, as happens, for example, in a system with periodic behavior? If we equivalence the state now and the state before, so we represent both as a single state, then we can end up with a loop in our causal graph, a closed time-like curve. And yes, in terms of the raw sequence of applying rules, these states can be considered different. But the point is that if they're identical in every feature, then any observer will inevitably consider them the same. But will such equivalent states ever actually occur? As soon as there's computational irreducibility, it's basically inevitable that the states will never perfectly match up. And indeed, for the states to contain an observer like us, with memory and so on, it's basically impossible that they can match up. But can one imagine an observer or a time craft that would lead to states that match up? Perhaps somehow it could carefully pick particular sequences of atoms of space or elementary events that would lead it to states that have happened before. And indeed, in a computationally simple system, this might be possible. But as soon as there's computational irreducibility, this simply isn't something one can expect any computationally bounded observer to be able to do. And yes, this is directly analogous to why one can't have a Maxwell's demon observer that breaks the second law, or why one can't have something that carefully navigates the lowest level structure of space to effectively travel faster than light. But even if there can't be time travel in which time for an observer goes backwards, there can still be changes in perceived time, say as a result of relativistic effects associated with motion. For example, one classic relativistic effect is time dilation, in which time goes slower when objects go faster. And yes, given certain assumptions, there's a straightforward mathematical derivation of this effect. But in our effort to understand the nature of time, we're led to ask what its physical mechanism might be. And it turns out that in our physics project, it has a surprisingly direct and almost mechanical explanation. One starts from the fact that in our physics project, space and everything in it is represented by a hypergraph, which is continually getting rewritten. And the evolution of any object through time is then defined by these rewritings. But if the object moves, then in effect it has to be recreated at a different place in space. And this process takes up a certain number of rewritings, leaving fewer for the intrinsic evolution of the object itself, and thus causing time to effectively run slower for it. And yes, while this is a qualitative description, one can make it formal and precise and recover the usual formulas for relativistic time dilation. Something similar happens with gravitational fields. In our physics project, energy momentum, and thus gravity, is effectively associated with greater activity in the underlying hypergraph. And the presence of this greater activity leads to more rewritings, causing time to run faster for any object that in that region of space corresponding to traditional gravitational redshift. Is that the right way around? I think so. More extreme versions of this occur in the context of black holes. Indeed, one can roughly think of space-like singularities as places where time ran so fast that it ended. And in general, as we discussed before, there are many relativistic effects in which notions of space and time get mixed in various ways. But even at a much more mundane level, there's a certain crucial relationship between space and time for observers like us. The key point is that observers like us tend to parse the world into a sequence of states of space at successive moments in time. But the fact that we do this depends on some quite specific features of us, and in particular our effective physical scale in space as compared to time. In our everyday life, we're typically looking at scenes involving objects that are perhaps tens of meters away from us. And given the speed of light, that means photons from these objects get to us in less than a microsecond. But it takes our brains milliseconds to register what we've seen. And this disparity of timescales is what leads us to view the world as consisting of a sequence of states of space at successive moments in time. If our brains ran 1,000,000 times faster, i.e. at the speed of digital electronics, we'd perceive photons arriving from different parts of a scene at different times, and we presumably no longer view the world in terms of overall states of space existing at successive times. The same kind of thing would happen if we kept the speed of our brains the same, but dealt with scenes of a much larger scale, as we already do in dealing with spacecraft, astronomy, and so on. But while this affects what it is that we think time is acting on, it doesn't ultimately affect the nature of time itself. Time remains that computational process by which successive states of the world are produced. Computational irreducibility gives us a certain rigid character, at least for computationally bounded observers, gives time a certain rigid character, at least for computationally bounded observers like us. And the principle of computational equivalence allows there to be a robust notion of time independent of the substrate that's involved, whether us as observers, the everyday physical world, or for that matter, the whole universe. So that's what I wrote. And I can perhaps try and take a few questions here. Let's see what we have. Jordi is asking, how does the notion of atoms of space square with Lorentz invariance? Commenting on loop quantum gravity, which is an older theory that is kind of not as low level, not as kind of machine code like as our models. The thing to understand is that it's a little bit complicated, and I've explained this in some detail actually many times over the last 4 or 5 years since I've sort of figured out how this works. Actually, I had already thought about this and figured out much of it in the early 1990s, and it's even in my New Kind of Science book. But basically, the point is this: if you can say that space consists of this hypergraph with all these atoms of space related according to the relations in this hypergraph. But what really matters to an observer who is part of this evolving hypergraph is the causal graph that says how every event, every updating event, is causally related to every other updating event. And the notion of a state of space is actually just something that emerges from the way that an observer parses that causal graph. And so the fact that one gets Lorentz invariance, one gets the idea that one can have different simultaneity surfaces, one can parse the structure of sort of space-time in effect in different ways. That's a consequence of the fact that the causal graph you get is you're just taking a causal graph and you're slicing it in different ways. Now, there's a subtlety there, because if you define a state of space by a particular foliation, a particular slicing, a particular set of space-like hypersurfaces of things you consider to be simultaneous states of space at moments in time, the fact that you can go through from one of those space-like hypersurfaces to the next, and you can change the way you pick the space-like hypersurfaces and expect the evolution to be equivalent, that depends on a property that we call causal invariance. That property is true for many underlying individual rules that you might just pick out randomly, but in the Ruliad, it's true in the aggregate of all rules. And so in the end, when you're sampling things from the Ruliad, it's inevitable that causal invariance has to exist. It's less obvious that it exists if you just say, I'm going to pick a particular rule. Although for many, even particular rules, you can see that there's causal invariance. And causal invariance is what ultimately leads to the fact that you get sort of equivalent laws of physics for different choices of these sequences of space-like hypersurfaces. It's slightly technical, but that's the basic story. And I think things that people back in the early part of the 20th century, there was this whole question of, is space continuous or discrete? That had been a thing that had been discussed since antiquity, and had been discussed, is space continuous or discrete? Is matter continuous or discrete? Is light continuous or discrete? One of the big results of physics and chemistry of the 19th century was the conclusion by the end of the 19th century that yes, matter is discrete, it's made of atoms. And then it became clear that you could think of light as being made of photons too. And in the first few decades of the 20th century, most physicists assumed that space would turn out to be discrete as well. And there were a whole bunch of the standard sort of famous names of physics who had these models of space in which space was kind of a set of discrete cells, kind of like a cellular automaton, lots of other kinds of models like that. And in fact, it's a frustrating piece of history because very little was written down because nobody could make it work. So it's actually quite hard to reconstruct what people thought, and I'm trying to make some effort to do that. But in any case, nobody managed to make that work because they kind of thought if you define space and time to have this sort of discrete arrangement, then you don't get Lorentz invariance because it's kind of like you have sort of a fixed infrastructure for the universe. None of that is an issue. By the time you get to things like our physics project and the kind of computational view of things and the notion of causal graphs and so on, all of those kinds of issues just sort of go away. It's when you have too rigid a predefined structure for space and time that there's trouble, and that you can't explain how you get a relativistic invariance and so on. But that's in the situation of our physics project, where really what's happening is it's really all about computational events that occur, that it's a much kind of floppier system that doesn't have that same kind of rigidity that seems inconsistent with relativistic invariance. Let's see. Peter comments here. I have a fundamental philosophical question that you can perhaps help with. A central aspect of time, Peter says, is its apparent motion. Something it seems is always moving. I don't think it's fair to say that it's purely perceptual. It really does seem characteristic as a central feature of time. Question then is, regarding our whole computational model, what exactly is it that compels or impels the state of the system to tick, i.e. progress from one state to another? Surely there is fundamental necessity for this to occur either computationally or ontologically, if indeed these are different for the Ruliad. If the next state is computed for the last, what is the nature or cause or reality of this moment of computing? It's an interesting question. It's kind of I think one version of that is kind of what breathes fire into the equations, so to speak. I actually wrote about this a few years ago in connection with the question of why does the universe exist, which is a highly related question. So as we build these computational structures, we think of them at first as a model, a representation of how the universe works. When we say we have an equation that describes the motion of the Earth around the sun, we don't imagine that the Earth is inside it. It's got a little computer that's explicitly, doing numerical analysis on a differential equation, working out the differential equation. It's merely that equation describes the observed facts of how the Earth moves around the sun. And so that's kind of the starting point for kind of typical models. Our model of physics is something more fundamental. It purports to just say everything about how the universe works. So now the question is, if that's everything about how the universe works, kind of what is it that makes that not just a model of the universe, but somehow the universe itself? So let me try and go through this. This is philosophically tricky, and essentially the point is that and this question about sort of the progress of time is, in some sense, from outside the Ruliad, there's no notion of progress of time. It is merely that as I think about what just happened, the causal graph that is abstractly created allows me to associate the events happening in my brain now with events that happened in the past. Now you say, what really runs the clock? What's making it tick forward? Nothing is making it tick forward. From outside the universe, there might be, if one could imagine being outside the universe, it could be an infinite time or a very large time between the moment when I think is now and the moment that I think was 1 second ago. It is merely an abstract set of connections between the state of the world 1 second ago and the state of the world now. It is not that anything is driving things from the state 1 second ago to the state now. It is merely that there exist connections. There exist these abstract causal connections. So when I internally, perceptually, am trying to understand what's going on, I am perceiving that sequence of connections. And so my model of things is to say, sort of time, I am progressing through time. But there's nothing that gives me kind of an overall clock. There's nothing that's driving the clock. It is merely that if you say, what is my perception of the state of things at what externally will be seen as a certain moment in time, I will say, well, this is a moment that has this happened last and this happened 2 seconds ago and so on. And it is merely this kind of the structure of things is merely that I have these collection of connections, and that my internal perceptual model is that corresponds to the progress of time. But there's nothing that's driving time from the outside. That it is merely a set of connections. It's merely a set of causal connections, and that which my perception is embedded in. And so I'm going to say time has passed. And by the way, for the universe at large, in a sense, time has passed in the same way. That was what I was talking about the universality of computational irreducibility. That's why my internal perception of time is consistent with the external perception of time, so to speak, the external progress of time in the universe. So that's an attempt at that question. All right, Daly is asking about what about moving backward in time? Has it now been rendered and essentially reducible? Now that as it has now been rendered and is essentially reducible. Okay, well, in a sense, whenever we remember, we are in some sense moving our perception backward in time. Notice, however, that what we remember is not everything. Our finite minds have already compressed and filtered the past to remember only some thin sliver of it. So it isn't the case that as we cast our mind back, that we are at that moment, we are effectively experiencing the past. We're experiencing only our memory of the past, which is a thin set of what actually happened in the past. Now, this question of whether sort of the future of us can be also our past is really asking whether in the state of the universe, something which is in our future is identical to something which was in our past. And the whole point is that with computational irreducibility and so on, it's one doesn't get it is as for a large universe, there just is, it's completely inconceivable that something which is the future will also be the past. If we were dealing with some simple idealized system, some kind of clock that's going tick-tock with a pendulum or something, or some spring or harmonic oscillator that's just bouncing backwards and forwards, then absolutely, in that idealized system, the past and the future can be the same. And in some sense, there's not really a passage of time for that system. It's just going back and forth, back and forth. And you can't really say time has irreducibly passed, because the future is just like the past in that case. So there isn't, to move backward in time, you have to sort of create in the future the states of the universe from the past. But that's not a feasible thing for a computationally bounded observer like us to do. And that's why we don't get to have something that is kind of like time travel in our universe. Let's see, Dan comments. In our physical universe, time is essentially a measure of change in the sequence of events. If there were no space-time, what would we be measuring? What would change, or what would events look like? Well, in our model of physics, the only thing in the universe is space. Everything about the universe has to do with the details of the structure of space. So it's kind of a little bit like if you're a fluid, like water or something, it's like there are all these molecules bouncing around underneath, but the things that are sort of persistent are things like vortices, eddies. And those eddy-like things are probably like the particles, like electrons and quarks and so on in our universe. Everything about our universe is just a feature of the structure of space and its progression through time. So in a sense, there is no universe without this underlying hypergraph, whose aggregate effect is to produce what we think of as space, and whose aggregate rewriting is to produce what we think of as time. So there isn't a way to disembody time from the actuality of the raw material, the infrastructure that represents our universe. Jaime asks, why can't time be accelerated? Can't we compute in an accelerated fashion, going through the computational steps in order to experience the future sooner? What forces the computation to take place in a given time? Yes, insofar as we can simulate the world, we can run on a faster computer, and that small slice of the world we can expect to simulate faster than it happens if we can capture enough of the details of the world to be able to know the things that we care about. In the end, the thing that we have to run that simulation on is itself a physical object, a part of the universe. So in the end, we're not going to, at a big level, we're not going to be able to do this, because we're essentially saying, can we predict the universe on a computer that is the universe? And we only get to predict it at the speed it happens. But yes, I mean, sort of the whole idea of simulation is to try and run on a faster computer, so we can, at least for these simplified versions of things that we're studying, we can kind of outrun the actuality of what happens and be able to say what will happen more quickly than it happens. The thing that kind of makes that often difficult is to know just what you have to include in the simulation and what you don't include, and to have the right boundary of what's included, and to not have the things that you aren't including affect the things that you are including and that you eventually care about the results from. Let's see. Jasper says, I've been trying to wrap my head around this lately. How does motion, let alone momentum, exist at all? How could it emerge from a timeless, infinite set of hypergraphs? Well, okay, what is motion? The possibility of pure motion, actually, I wrote a piece about motion a little while ago. Maybe I should do a session talking that through. But the possibility of motion is not an obvious thing. The fact that you can take an object and move it and expect it to be the same object is a non-trivial fact about underlying physics. It isn't always true. If you have space-time near a space-time singularity, any object that you think of as a coherent object, you know, a glass of water or something, will be, the space in which it is embedded will be so torn apart by that singularity that you won't really be able to say, I moved the glass of water from here to there, because the thing will have sort of been shredded when it gets to the there. So the possibility of pure motion is something that is a non-trivial feature of a model of physics. So the primary carriers of pure motion in the universe are particles, like electrons and quarks and so on. They have the feature that an electron has, if you take an electron and it moves, it's carrying its identity without change to another place. And it's carrying its identity through space and through time, and it's still just an electron. One of the big mysteries of physics is why all electrons are the same. By the way, in addition to particles like electrons and quarks, the other big thing that seems to be capable of pure motion is a black hole. A black hole, which can be of sort of any size, again, maintains its identity as it moves through physical space and through time. And actually, my own guess is that there's an incredibly close correspondence between black holes and particles like electrons. And there's all sorts of mysteries when you have a black hole and the black hole forms and it crushes some whole civilization that was had a bunch of planets around a star or something into the black hole. But inside and that can still, the sort of vestiges of that can still exist inside the black hole. But to outside the black hole, all you see is the event horizon of the black hole. All you see is that things can't get out of the black hole, and you just see sort of the outer properties of the black hole. My guess is the same is true of electrons. While it seems that every electron is the same, it probably is the case that somehow inside each electron is a whole trace of the history of that electron. It's just not something that we perceive from outside the electron. But the fact that electrons can exist, there can be carriers of pure motion, is not a trivial fact. It's something that you have to prove in a model of physics. And so in a sense, motion is like, for example, the eddy in the fluid. It is not that the underlying stuff from which the fluid is made is sort of moving over a large distance. It's that this collective effect, which we can perceive as being this swirling fluid, that swirliness is moving through the fluid. It's not that there's some motion of the individual molecules that's slightly different than it would be sort of on the average, but the thing we are identifying, this thing that we then say is undergoing pure motion. The eddy is moving through the water or whatever. And so it's the same, I think, for our carriers of pure motion in our universe, particles and so on. By the way, I mean, there's a lot of very interesting kind of correspondences with this notion of pure motion in different kinds of media. So, for example, one of the more exotic ones is pure motion in the Ruliad, where sort of dotted around the Ruliad at different places in the Ruliad are these effectively minds that exist at different places in Rulial space. And the question is, what's the notion of pure motion that goes from sort of the position of one mind in the Ruliad to the position of another mind? Every different mind has a different sort of point of view about how to think about the universe. But the thing that we get to kind of transfer between minds is, in effect, I think, what we think of as the notion of a concept, so to speak. In other words, in our brains, we've got all these kind of nerve firings going on. My version of the nerve firings that represent a cat will be different from your version of nerve firings that represent a cat. But somehow we can package up some robust thing that represents this abstract notion of a cat. And we can, for example, use the word cat, and communicate that concept. We can essentially send that concept, and that concept can undergo pure motion through Rulial space, going from one mind unchanged and arriving at another. So the one mind is sort of packaged up that notion of a cat that came from a bunch of nerve firings to this single concept, which then can be unpacked by the other mind. So there's an idea of pure motion in places other than physical space. I'm trying to understand actually the idea of pure motion in branchial space, and I don't think I fully understood that yet. I kind of think that motion in branchial space is related to virtual particles, but I'm not completely sure how that works. I mean, just to explain that, for sort of that's kind of physics from nearly 100 years ago, the notion of virtual particles is the following. When you have something like an electron, you have this electron, you produce it, it moves through physical space, that's all good. And it has a particular relationship. It has a particular mass, any particular electron has a certain energy, a certain momentum, and so on. And there's a certain relationship between its energy and its momentum, E squared equals P squared plus M squared, and so on. All those kinds of things with some, it's actually, what is it? E squared equals P squared C squared plus M squared E to the C to the fourth, where C is the speed of light. That's the version of this. Well, it turns out that one of the features of quantum mechanics is the particle that doesn't last long from when it's emitted to when it's absorbed doesn't have to exactly obey that relationship between energy, momentum, and mass. It can have an effective mass, or effective, which differs from the actual sort of everyday, the particle is out there on its own mass. But the amount of difference, it's governed by the uncertainty principle. It tells one kind of how much one can be uncertain about the mass if it's only lasting a short time. So virtual particles are particles that are emitted and then absorbed, and because they last only a short time, they can have things like effective masses very different from the ordinary, everyday, it's lasting forever type mass of a particle. And so forces like force of electromagnetism, or even probably the force of gravity, although that works slightly differently, but force of electromagnetism, or the force that holds nuclei together, the strong nuclear force, these are all can be thought of as due to the exchange of virtual particles between things like electrons or things like protons or whatever. And those virtual particles are effectively, a particle like a photon, a virtual photon is emitted. The virtual photon may not be massless. An ordinary photon is massless, but a virtual photon doesn't have to be massless. But that virtual photon might be absorbed a billion billionth of a second later. And but it can sort of violate the usual idea of what the mass of a photon is supposed to be. I suspect that, so that phenomenon is a fundamentally quantum mechanical phenomenon. I suspect that it is related to motion in branchial space. And my guess is that a virtual particle is a kind of thing which, like an ordinary particle, like an electron, can sort of move without change in ordinary physical space. That there's a similar kind of idea for moving in branchial space, for basically being able to go roughly between different branches in this multi-way graph, and that's kind of that sort of knitting together different branches in the multi-way graph in that way. But I don't know how that works exactly. Something to figure out in the future. But it's that just gives some idea of how motion might work in different cases. Momentum, by the way, is well, there's both momentum of an individual particle. There's also sort of the bulk amount of momentum that exists in a given region of space. And it turns out in our models, there's a very simple interpretation for that. So essentially, both energy and momentum are associated with the density of activity in this hypergraph. So lots of rewriting in the hypergraph means lots of energy in that location in the hypergraph. More precisely, you have to draw these causal graphs that represent sort of whose nodes are the events in the hypergraph and whose edges are the causal relationships between those nodes. If you take that causal graph and you slice it in a space-like direction, then the flux of causal edges, the number of causal edges that poke through that space-like hypersurface, that corresponds to the energy density associated with that region in space. If you take another slice, if you take a time-like slice that's orthogonal to the space-like slice, so the time-like slice is kind of slicing in a direction where things go progressively with time, the space-like slice is slicing across that to things which can be simultaneous in time. You take a time-like slice, the flux of causal edges through time-like hypersurfaces is momentum. So it's kind of a very clean definition. And by the way, that way of thinking about it explains why the relativistic transformation for position and time has the same form as the relativistic transformation for momentum and energy, which is something which in the original sort of setup of relativity, well, original and current setup of relativity in traditional physics, you just have to assume that both space-time and energy momentum transform as four vectors, that they transform in a certain way under Lorentz transformations. In our models, that's something that actually emerges from the model. It's not something you have to build into the model from the beginning. Let's see. Okay, Mark is asking, can the idea that every branch has a merge be expressed with something like Gauss's law for electromagnetism, that the divergence of time is zero, and that this is a conservation law for reality? That's an interesting thought, actually. I mean, causal invariance basically says that every branch has a merge. What is the relationship between kind of the flow in branch time, which is the analog of space-time for time and branchial space? What is the equation of motion in branchial space for those branches? That's an interesting idea. My guess is that if you work that through, that you will discover that it is equivalent to the path integral or to equations of motion like the Dirac equation. But it's an interesting idea. I have not thought about it in that way. It's a good idea to think about that. I should think about that. Thank you. Well, you should think about that. It's a good thing to think about. There's probably something kind of cool there. I have not thought that through. I mean, as I say, the causal invariance does lead to sort of an equal number of branches and merges. So there is, in some sense, a conservation of reality that implies. But I haven't thought that through. Thanks. Let's see. Brady asks, what would reversible rewrite rules be like? Would this be different would this affect the way we perceive space? Well, this whole business about causal invariance means that in aggregate, there is a certain kind of reversibility. So it's important for sort of conservation of probability that there is an overall reversibility. But in terms of microscopic rules, rewrite rules, that's actually pretty complicated. The notion of reversible hypergraph rewriting is something that is a little difficult to define, because the state of the system has all these sort of separate, you can have separate, disconnected pieces of hypergraph and so on. It's a little tricky, and I'm not sure that I have a great definition yet of that. Let's see. Prutz asks, can we compare the lengths of time that have elapsed in different threads of time? Is the comparison unique? Basically, I think that sort of the universality of computational irreducibility will make those different kind of time progressions be equivalent in the same way that heat in different objects is somehow equivalent, that the way the energy is represented in heat is the same as a result of essentially computational irreducibility. So I think that's the case, that different branches, different threads of time, I think inevitably end up with equivalent kind of rates of progression of time in them. All right, looks like that was all the questions we had. It looks like I got to go back to my day job. So thanks very much for joining me. You can find the text or what I was talking about the notion of time on my collection of writings, and look forward to talking to you again on another live stream in the future. Bye for now.